It's now time for the next talk by Draskovic, Architecturing and Securing Internet of Things Platform in Go. Thank you.
So hello everybody. Today we will talk about Internet of Things and how do you implement those platforms in Go. My name is Draskovic, and I come here in front of the one open source project called Mainflux, which has the ambition to do Internet of Things, cloud, to which the devices should be connected, and that can be reused then within the industry to solve those kind of problems. So you can check out the project at mainflux.io or use the Twitter handle Mainflux. My background is mostly in the hardware development, and I had to build up the knowledge up the networking stack in order to understand how those constrained devices can be connected to the internet. So I'll briefly go through the outline of this talk. We'll talk about Internet of Things and cloud, we have to have some prerequisite knowledge because it's a very vast subject. So we'll talk about, I'll just touch briefly of what do I consider when I say Internet of Things, and then we'll examine the architecture of one typical Internet of Things backend or middleware solution, and I will try to explain why some decisions have been made. And Mainflux is a good example because it's a relatively mature project. We've been working on this for almost 2 years now. So there is a lot of lessons that have been learned on the subject that I want to share with you. So before I go on with the presentation, I just want to check out how many of you have a general idea of what IoT is about, of what Internet of Things is. Great. So I can go very fast through this. The other question is, has anybody tried to implement a solution in Go of Internet of Things? Great. So we'll focus on this subject, and we'll have, hopefully you will have a lot of takeaways from this. So this is an IoT talk, but it actually means that we will touch a lot of subjects like embedded software, radio frequencies, network protocol, server architecture. We really need to have at least basic knowledge on all of this in order to understand the requirements and constraints and decisions that are behind the solutions that are running in the back end. So very briefly, you take things, you connect them to the internet, and it's easier said than done. And when I say things, I mean sensors and actuators. So everything that you connect, you can basically divide in 2 categories. Either you are sensing and having some telemetry measurements pushed as a messages to the clouds and towards applications, or you have an actuator. That means that you are sending actual commands like smart lock or some robotic arm, something that has to be moved, etc. And the main idea behind IoT is to collect all of this data, execute analytics, apply maybe machine learnings, and create new values and new services that don't exist today and that are not possible today because internet is not still present in all of these kind of physical objects. So what are the approaches? There are centralized and decentralized approaches. Decentralized are something that we are seeing appearing more and more, becoming more and more interesting, but it's hard to do. So Qualcomm and Intel are proposing their solutions that are directly peer-to-peer. That means that, for example, home appliances can talk one to another. Your TV will have some kind of standard compliancy and be capable of talking to your fridge. There are some other solutions that are emerging now that are based on the blockchain. I saw recently one interesting project called Iota Blockchain, which is like a blockchain generation 2. It's more directed as cyclic graph, as they call it. There are decentralized solutions to look for, but practically everybody is building a centralized solution of, when I say everybody, of those big industry, big companies like Amazon, IBM with Bluemix, etc. So it's easier to implement, and I will give an example of this kind of architecture. So this is a typical cloud architecture regarding IoT, and that is that as a middleware, you have your backend solution, which is the subject of this talk. But just for you to get a picture, on the left-hand side, there are some devices. It's not very visible, but those devices are connected to the cloud by some Internet of Things protocols. You cannot see this, it's in white on this slide, but and on the other, let's say on northbound interface of your middleware, you will have the applications, and the cloud will bridge those messages that flow from devices to applications and vice versa, and will also provide you with some other very useful functionalities like time series database or some rules engine where you can have a complex event processing, etc. So I really want to go very fast to what are those things before we really jump into the Go solutions, and hopefully to understand the requirements of those for this kind of networks. So these are very constrained devices, very small. This is a small device, small computer, if you want, developed at the University of Michigan, which has a small solar cell and can be so power perpetually work just in the ambient light. It doesn't have a battery. So this is a Hitachi Rf Id Chip. So there is like it's about, you see the size, and this thing is capable of storing hashes and doing radio frequency, sending messages. So you can imagine how it's difficult to program those devices, and what are we dealing with? How many memory do we have? This is not the ordinary PC, not an ordinary telephone where we can be, like we have comfort. These are really devices that are constrained in flash and especially in RAM, because they are usually using SDRAM, and it's very expensive. And it's also important to remember that power consumption is like a paramount for these devices, because they have to be autonomous, they have to be, mobile, and they are battery powered, but with relatively small batteries, often with coin cell batteries or solar powered. Because they have so little amount of memory, your classical networking stack will not fit into this memory. So we have to make some engineering decisions to make this kind of connections work and work in a secure manner. So even TLS becomes a problem, and without TLS, we cannot really have security. What is proposed is to use often UDP instead of TCP because it's more lightweight, but then it imposes another problems, because many of telecom operators are blocking UDP through various firewalls, and also you have to, it's more difficult to punch those holes through the firewall from the client side, because all the firewalls are closing very often UDP connections like in 30 seconds or so. So it's something to have in mind. Also, when using TLS security, it's advisable to use elliptic curve cryptography, Diffie-Hellman. It's smaller in size. It's much smaller in size than classical RSA cryptography, and use alternative or new ciphers to enable those kind of cryptography. And as you know, the cryptography is very intensive software-wise, and those are very small devices with very constrained CPU power. So those microcontrollers often have a dedicated hardware unit that would do the encryption algorithm. So this can be reused. But every burst of radio signal on the ether is very power hungry. So that means what costs you most, it's like sending those messages through some kind of radio frequencies. Either if it's usually not Wi-Fi, because Wi-Fi is very power consuming, but it's either slow pan or Bluetooth low energy or Zigbee or something like this that we have in the industrial networks. So those devices actually sleep most of the time. Those are sleeping sensors. And this is also very important to note, and we will see later what kind of decisions this imposes on building IoT middleware solution. And what you want to do is really keep the messages short, because it's TX, so radio transmission, and RX, radio reception, that is wasting the most of your battery. And you want these devices to have practically a lifetime of 5 to 10 years, and then you never swap the battery. You install these devices in some industrial environment, and it just costs you much more to go and change device by device than just you must presume the battery will never be changed. So you must be very careful on this. And so when we saw these constraints, when we have these constraints in mind, we can now explain why some protocol, this imposes certain networking protocol choices. So the first impulse would be, let's use WebSocket, because it's bidirectional communication. It's perfect. We can send real-time information and monitor the changement, for example, of temperature in the real time. But this doesn't work, because these are WebSocket is very complex protocol. And so should we fall back to HTTP then? But it's the same problematics. There is a lot of overhead in the messages. There is a lot of redundant information that is sent through HTTP protocol, and it becomes complex for small devices. So what are then the protocol choices? It's MQTT and co-op for devices. And for applications, it's perfectly fine to use traditional approaches with the HTTP and probably with WebSocket. So MQTT is a protocol made by IBM in 70s, which is having its revival today, and it's very suitable. It's been made by IBM for gas line installations, and it's very suitable exactly for those kind of devices that have the intermittent connection. So they go for a long period of sleep, and then wake up, send some short messages, and you have to take this into account, that you will have like millions of devices, but they are coming and going very often, and they are establishing connections, and you have to have tools that will allow this and have some kind of persistence of those messages, so the message can be delivered once the devices wake up and ready to receive the message. Co-op is a new protocol for Internet of Things that is similar to HTTP, but with a much shorter messages. So it's a RESTful base, and in the co-op philosophy, every small microcontroller device, some of those microcomputers that I showed, are basically small servers that can accept commands, or you can read the messages from them, and they have also some kind of observe mode from which even this server can do a server push of the information. So yeah, when we use Internet of Things, we would prefer to use MQTT or co-op. So now, having this information, these requirements in mind, let's see the example of Go implementation of one middleware that can handle these kind of use cases, these kind of devices, the devices that talk these kind of protocols and have the problems of intermittent connections, short messages, low power, etc. So what we propose is an architecture based on microservices. This is how we started building a project called MainFlux. And those microservices are presented on this slide. And I will go in a bit of details before jumping into the code and showing you what kind of Go code we could use for implementing this kind of solution. So the central part is basically a core which talks to the MongoDB. You can put any other database in here, and maybe some time series database like InfluxDB would be more suitable. But Mongo was easy for prototyping, so we took this one. The core service is accepting HTTP connections and have beyond a pure messaging role, also the role of the system administration. Mqtt broker has also a possibility, like many Mqtt brokers that exist today, have possibility of being a WebSocket server. So you can reuse this because it comes with the broker, and then you can enable WebSocket connections for the applications also. Very important part is the Authorization Server that is basically here to check every request, and you have to have in mind that these are not only HTTP requests, but these are also MQTT messages that are sent, and that this MQTT is pure TCP protocol. And eventually in the future there will be a co-op, and with co-op the thing complicates it even more because it's UDP protocol, so you have to take this in mind also. Authorization Server is connected to Redis just to stock some information about user logins, because you will have some access control to your devices. And very interesting part is how do we bridge those protocols, because they have to talk one to another. So application is, for example, knows how to speak WebSocket, but devices know only MQTT protocol. We use a NATS broker, which is, in my opinion, one of the most beautiful example of Go engineering. Take a look at this code. It's open source, and it's a fantastic messaging broker that can handle over 10 million of simultaneous connections. On the reverse proxy side, we choose Nginx, which was, I will explain the reason for this choice, because there are Go solutions that can be evaluated and that were evaluated, but we saw some problems. And from this point on, I will go into details. So device and applications connect to the reverse proxy, which is your first line of defense, which forwards all the requests to the authorization server. If the authorization server responds 200 OK, then you can proxy this message or command or request to the appropriate protocol server, which can then persist it in a database and bridge it to another protocol, right? So reverse proxy, let's start with this one. It is here for load balancing, high availability, fault tolerance, etc. So very traditional, classical approach. You have to, you want to have a reverse proxy that can spawn all those servers behind in order to have a scalable solution. But it does one more thing. It does SSL termination in this particular case, just because it's easier, and because probably your backend services are within your trusted data center. So it's easier to have this SSL termination in one place because you have many protocols that are different on the transport layer. MQTT is TCP, co-op is UDP. For UDP, you cannot use TLS, you must use DTLS. So Nginx knows how to do this kind of checking and authorization. It does some kind of policy enhancement point role where it, as I said, intercepts the request, forwards them to the authorization server. And here we come to this Go solution that I mentioned. A traffic load balancer and reverse proxy is a wonderful proxy that we evaluated. It's very modern, very powerful, and it has some benefits of running Docker containers behind, and without reloading the server, you can have a changed configuration as those Docker instances are spawned, and your configuration changes as you scale up and down horizontally. But there is still some bugs open that prevents us in traffic to forward these authorization requests to our authorization service, and it's really a deal breaker. We could not use it for now. And also, as I mentioned, different protocols, TLS, DTLS, traffic doesn't have yet this kind of stuff. And you probably need some kind of plugins. Traffic is young server. So at least maybe as a takeaway, remember that a reverse proxy is there to intercept the requests from different protocols and forward them to the authorization server. Now about the authentication and authorization itself. So authentication can be done in many ways, but for devices, it's very suitable to use client-side certificates, which is kind of unusual in a RESTful API approach, for example, where you would use a token, API token, to access your backend services. But it's very consuming to deliver a token each time you want to talk to your backend service. And for the higher security, you would prefer to burn this certificate, authority, root certificate, or intermediary certificate into the device itself. This, of course, complicates the architecture because you have to issue this client certificate authority every time. And this is what we worked on also in the main Flux, because there are a lot of services, and this particular authorization server is capable of issuing a certificate, a client-side certificate authorities, something very similar to what Amazon IoT service does. So the code in Go is already there from recently. It can handle elliptic curve, Diffie-Hellman type of ciphers, and you can issue those certificates for the clients and for the devices. If you want to go with a token, then Go has very nice support for JSON Web Tokens. And since JSON Web Token is a pure token, pure JSON, which is encrypted, within it, it has a scopes field in which you can even say, okay, this device can access, you can do some kind of access control list within a token itself. This saves you looking up in the database of to which resources this device can access. Because all you have to do is to decrypt the token, and you can do this directly on the reverse proxy, and then you will know practically the information about access control. So you have some benefits with JSON Web Tokens, but also there is a lot of drawbacks. As I said, you have to deliver the token each time you communicate with the backend server. About authorization itself, I mentioned the scope JWT, but the drawback is that with JSON Web Tokens, you usually don't have revoke. Because if you want to revoke those tokens, then you have to hold the state in the database. And this practically defeats all the purpose of having a stateless token in which you encrypted, in which you wrote your access controls. If you have to look in the database every time you have a request, then practically you don't have to go through all this trouble of issuing a long JSON Web Token. What you want to do is to give it a very short time to live so it expires fast. So it really serves you for a session, and it's very suitable for the application. But for the devices, it's not so suitable. And there is a perfect Golang tool for the authorization itself that I really love. It's called Ladon. which goes after the Amazon AWS IAM policies philosophy. So you define an access control to the resources, and you stack them one over another and make a superset of the resources to which your device or your application can access. And with this, you can make a really fine-grained authorization. And it's very good for this authorization role, as authentication would be done probably by client-side certificates, as I explained. So about HTTP API, so there is not much mystery. Go is kind of don't like frameworks, right? So we evaluated several frameworks, and the lessons is that Negroni is very much like a super lightweight framework that just abstracts the minimal, and it's idiomatic and removes clutter, and it gives you kind of access to the some kind of middlewares that you want to reuse. Very important, in my opinion, is that it keeps a signature of the handlers as they are, from the standard library. So you can write the tests as you used to, and you don't have to change the tests because you're using some other router. And this is extremely important for us. And another very, let's say, a specific thing that is used in this kind of communication and this kind of messages is the model of the message itself. And SendML from Cisco, this is a Go package, so it's already been done open sourced, is a nice package that models the message in both JSON format, which is, so if you want to use JSON serialization, or binary serialization called CBOR, which is also IETF standard. Takes a little less space, and the messages are shorter. Again, important for IoT devices. And those SendML messages look like this. You have some base name, base time, base unit, and then you report the measurements of the, for example, current at the relative moment of time with the value 1.2, value 1.3. So you see even the name of the fields, they try to shorten them. Even though JSON serialization has a lot of overhead, we try everything that is in our power to make those messages shorter. So there are some choices that we use with the experience. Configuration in TOML is just much more simpler parser-wise. We use Glide for rendering so that you simply have all the dependencies inside the main repository, and we really love Docker Test. Docker Test is a fantastic package that lets you test and do the mockups in the database. So another rant I want to do is finding a good MQTT broker. It's very difficult in the Go community, and I'm really hoping that some good broker will appear. For the moment, I mean, we evaluated Erlang solutions, which were very promising, as you would expect millions or maybe billions of those devices to be connected and have a simultaneous connections toward your backend. So at the same time, very hard to handle for a lot of languages, not for Erlang, Elixir, and not for Go. But we have to settle with one MQTT broker from Node.js, because a good broker in Go is still missing. There is one called SurgeMQ, taken by Influx Data Company, which is the author of Influx DB. But the project is on hold, even though it has really impressive benchmarks, which is not surprising for Go. So it's very efficient, and at the same time, it can accept a lot of simultaneous connections. The lessons learned with connecting to the MQTT broker with suitable to scalability. So the MQTT broker has like a joker topic, which is hash. to which you can connect and get all the messages that come from the broker. This is anti-pattern that should be avoided, because when you scale and you bridge a lot of those brokers, you don't want that all the messages go through one, they end up in one broker in the end. So you defeat the whole purpose of scaling. The other problems that you are facing with MQTT is that you don't know who actually is the publisher. MQTT protocol doesn't give you this on the client side. When you receive the message, you don't know which device sent it. So this is one of the reasons we are also using nuts and putting this extra information into the backend. There is a loopback in MQTT. When you are subscribed to one topic, all that you send, you receive. This is not good. And we do the bridging of the protocols using nuts. So ideally in this architecture, as I mentioned, you can send by HTTP, receive by MQTT, send by WebSocket, receive by co-op, etc. So we must do this kind of bridging because we have devices that speak different protocols and applications that are capable of speaking different protocols. So main Flux can do this. And in the end, I want to mention CLI. This is no surprise. You know, Go has perfect packages like Cobra that can do this kind of stuff. I will go very fast just about deployment. Docker Compose up, you have all the server running. So all the Docker images are built, put on the Docker Hub. You just take one file, it's Docker Compose YAML, and you do a Docker Compose up, and all those microservices will be automatically downloaded for Docker Hub and spawned, and you can have easy deployment of this kind of backend solutions. And then you can do the Kubernetes to go deeper into this kind of scalability. So how does it work? Just a quick examples. You want to create some devices into the system. You provision them by sending a post to /devices. And there are also notion of channels. So main Flux is simple. You have only two models. One is device. So you provision device into the system, to which device will post its messages. And then you have a channel. And those devices, actually, many devices can speak to one channel, and application can get this information from a channel. So here is an example of posting SendML, as I mentioned, message to a certain channel of this hash ID. And then on the other side, for example, some other application or some other device gets these messages from a channel. And as I said, it's bridged. So you can also, to the same channel, you can post from a device, from an MQTT device, for example. And the application will get, even though it's connected to the WebSocket, which is very usual for mobile application, for example. And this is, from the technical perspective, it's, as you see, there were a lot of stuff. I just want to mention in the end about the project organization itself. So it started from this hardware project. This Go backend project started from a hardware project called VIO, which is open hardware project. And we needed a way to connect those kind of electronic devices to the cloud and to the internet, and to be capable to control those devices from the different geographical locations. The project is open source. It's Apache 2 licensed. So you are very well invited to contribute, and we do gladly accept pull requests. So thank you very much. This will be all for the talk.
Thank you.
If we have some more time left, we can go through the question and answers.
Yeah, we are. Okay.
Hi. So given the fact you are stopped using wildcards in MQTT, which are indeed the most difficult thing to do because they don't scale, did you ever evaluate trying to use a AMQP protocol instead of MQTT? Because we are, basically, I'm from Arduino, and we faced exactly the same issue. So we were really evaluating to try to support multiple protocols, depending on the device you get, how much powerful it is. But it looks like AMQP can be used even in very small devices. What do you think about that?
So AMQP is really an industry standard for queuing, and we did try to evaluate it quickly with the RabbitMQ, which is great Erlang broker. Why? Because RabbitMQ has a very nice way to add security as a plugin, and also to add Mqtt plugin if you need it. But it was too heavy for the devices that we have in mind. So when we talk about 15 billion of devices, which was some predictions by Gartner in 2020, now they diminished it to around 21 billions. So it will be like 20 billion of very extremely small, like smart dust, extremely small devices. And this is what we want to take into account. And you really don't have so much choices. Mqtt is very well suitable for this. It has support for intermittent connections. It has quality of service support specialized for this kind of devices. It has some other cool features like last will and testament, etc. So it's much more adapted to this kind of problem than Mqtt. And co-op is more modern and probably more adapted.
There was another question around there before. Okay, so then it's going to be your turn.
Thanks. How do you handle the situation when one device misbehaves and begin to flooding the database with metrics?
So actually it's handled through the Nginx plugins. You have some kind of data rate control on the Nginx itself, but it can really you can always identify you identify which device is sending the messages, and then you limit the rate. Right. Right, and this is just a pure configuration because Mqtt brokers do have this kind of data rate limiting. They have built this inside, so you can say it's like engineering decision. There is no rule. You evaluate your backend solution, and then you say, okay, I will limit to this number of messages per second, for example.
I suppose most of the main Flux code runs on servers, but you don't run Go on the devices itself, do you?
No. On the devices, it's really, these are devices that you can imagine. A typical device would have about 32 to 64 kilobytes of RAM. So it's like we are in 2017. Those are microcomputers that have like a few kilobytes of RAM, and it's very hard to even, sometimes even in assembler, to write the code that will do all the network handling, etc., TLS, encryptions, etc. So the industrial software for this kind of devices, it is always written in C. When you have some kind of more powerful boards like Raspberry Pi or something, this starts to resemble like a small PC, and then of course Go is a perfect candidate for this kind of applications. But this is not really. Then it becomes like a traditional network, not really an IoT. So yeah, so it's usually written in C, bare metal, no operating system. Eventually, some real-time operating system that can have today around 4 to 10 kilobytes of memory, and just to give you a scheduler, so you can handle networking stuff without blocking. So if there are,
I guess we have time for another question. Okay.
Okay, thank you very much.
Thank you.